Welcome everyone to this Reservoir Simulation Masterclass. In this tutorial, we will learn how engineers and scientists predict what happens deep underground, where we cannot directly see fluid flow, pressure movement, CO₂ migration, or hydrogen storage behavior. Reservoir simulation is like building a digital laboratory of the subsurface. Instead of guessing what happens underground, we use physics, numerical models, and computer simulation to forecast future behavior. By the end of this video, you will understand the basic physics, the workflow, and the real applications in oil and gas, CO₂ storage, geothermal energy, and underground hydrogen storage. Before we go into the details, let us look at the roadmap. We will begin with the basic question, why do we need reservoir simulation? Then we will learn the main reservoir properties, such as porosity, permeability, pressure, and saturation. After that, we will introduce the core physics, mass conservation, and Darcy's law. Then we will convert the physical reservoir into a grid model and solve the equations step by step. Finally, we will discuss advanced applications, including CO₂ storage, hydrogen storage, uncertainty analysis, geomechanics, digital twins, and AI surrogate models. Reservoir simulation matters because the subsurface is complex, expensive, and uncertain. We cannot easily see what happens several kilometers underground, but we still need to make important decisions: where to drill, how much fluid to inject, how much pressure is safe, and whether CO₂ or hydrogen will remain trapped. Simulation allows us to test many scenarios before real field operations. It helps reduce risk, improve recovery, optimize storage, and support safer engineering decisions. In simple words, reservoir simulation helps us see the invisible underground system before making expensive choices. A reservoir is not a large empty cave. It is usually a porous rock formation containing tiny pore spaces. These pore spaces can store water, oil, gas, CO₂, or hydrogen. Above the reservoir, we often need a sealing layer called caprock. The caprock prevents upward leakage and keeps the fluid trapped underground. The behavior of a reservoir depends on rock properties, fluid properties, pressure, and geological structure. In reservoir simulation, we represent this underground system digitally so that we can predict how fluids move inside the pore network over time. Porosity tells us how much empty space exists inside the rock. If a rock has high porosity, it can store more fluid. If it has low porosity, it has less storage capacity. But porosity alone does not tell us whether fluid can move easily. A rock can have many pores, but if those pores are not well connected, fluid movement may still be difficult. That is why porosity is mainly related to storage capacity. In CO₂ storage or hydrogen storage, porosity helps us estimate how much fluid the reservoir can hold. Permeability tells us how easily fluid can move through the rock. If pores are well connected, the rock has high permeability and fluids can flow more easily. If the pores are poorly connected, the rock has low permeability and fluid movement is slow. This is one of the most important properties in reservoir simulation. High permeability can lead to faster pressure propagation and faster plume migration. Low permeability can limit injectivity and production. Therefore, permeability strongly controls how the reservoir responds during injection, production, CO₂ storage, or hydrogen withdrawal. Pressure is the driving force for fluid movement. Fluids move from high-pressure regions toward low-pressure regions. When we inject fluid into a reservoir, pressure increases near the injection well. This pressure disturbance then spreads outward through the reservoir. The pressure response can move faster than the actual fluid front. This is very important. Even before CO₂ or hydrogen reaches a distant area, pressure may already affect that region. Therefore, pressure prediction is critical for injection design, storage safety, well performance, and induced seismicity risk. Saturation describes how much of the pore space is occupied by each fluid. For example, part of the pore space may contain water, part may contain oil, and part may contain gas. In a simple water-gas system, water saturation plus gas saturation equals 1. During injection, saturation changes with time. The injected fluid gradually replaces or displaces the original fluid. Saturation is very important because it tells us where the injected fluid actually goes. For CO₂ storage, saturation describes the CO₂ plume. For hydrogen storage, Saturation helps us understand storage volume and recovery. Darcy's law is the foundation of flow in porous media. It tells us that flow depends on permeability, pressure gradient, viscosity, and flow area. Higher permeability means easier flow. A stronger pressure gradient means faster movement. Higher viscosity means the fluid resists movement and flows more slowly. Darcy's law is powerful because it connects rock properties, fluid properties, and pressure into one simple physical relationship. Almost every reservoir simulator is built on this idea. If we understand Darcy's law, we already understand the heart of reservoir simulation. Now we connect the physics to the simulation workflow. First, we build a geological model. Second, we define the governing equations. Third, we divide the reservoir into grid cells. Fourth, we solve the equations numerically. Finally, we generate forecasts of pressure, saturation, production, injection, or storage behavior. The computer does not know the reservoir by itself. We must give it geology, rock properties, fluid properties, well controls, boundary conditions, and time schedules. Simulation is simply physics solved cell by cell and time step by time step. The most important rule in reservoir simulation is mass balance. What enters the system minus what leaves the system equals what accumulates inside. This is the same idea as a bank account. If more money enters than leaves, the balance increases. In a reservoir, if injection is greater than production or leakage, mass accumulates and pressure may rise. Mass balance ensures that the simulation is physically meaningful. Without mass conservation, the model may produce unrealistic pressure or saturation results. Therefore, every reliable reservoir simulator must carefully satisfy mass balance. The conservation equation is the mathematical statement of mass balance. It says that accumulation plus net flow plus source or sink terms must balance. In reservoir language, source terms are injection wells, and sink terms are production wells. The accumulation term tells us how much mass changes inside the grid block. The flux term tells us how much mass moves across grid block boundaries. This equation may look abstract, but the meaning is very practical. Imagine one grid block around an injection well. The well injects fluid into that block. Part of that fluid increases pressure and saturation inside the block. Another part flows outward to neighboring blocks. The conservation equation ensures that these quantities are consistent. For single-phase flow, the equation may be relatively simple. For multi-phase flow, each phase has its own mobility, saturation, density, and relative permeability. For compositional simulation, we may track components rather than just phases. For thermal or geomechanical simulation, additional equations are added. But the foundation remains the same: conserve mass, compute flow, and update the state variables over time. Now that we understand conservation equation, let us move to grid discretization. A real reservoir is continuous, but a computer cannot solve equations at every point in continuous space. Therefore, we divide the reservoir into grid blocks. This process is called discretization. Each grid block represents a small volume of rock with averaged properties such as porosity, permeability, pressure, and saturation. The grid is extremely important because it controls how the simulator sees the reservoir. A coarse grid runs faster but may miss important features such as thin barriers, sharp fronts, or near well pressure gradients. A fine grid gives more detail but requires more computational time and memory. In real projects, choosing the grid resolution is a balance between accuracy and efficiency. This slide shows the idea of breaking the reservoir into smaller cells. Once the reservoir is discretized, the simulator can apply conservation equations to each cell and calculate flow across the faces between neighboring cells. The next question is, how do we approximate derivatives and flow terms numerically? One common answer is the finite difference method. Now that we understand grid discretization, let us move to finite difference flow. Finite difference flow is one of the classic approaches used in reservoir simulation. Instead of treating pressure as a continuous function, we approximate pressure differences between neighboring grid blocks. If pressure in one block is higher than pressure in the next block, Darcy's law gives the flow direction and magnitude. This is repeated across the grid. The figure on the slide shows a central grid block connected to neighboring blocks. We can think of each connection as a small flow pathway. The simulator calculates transmissibility, pressure difference, mobility, and flow across each connection. Then it updates the pressure and saturation in each block based on conservation. This may sound simple, but when we have thousands or millions of grid blocks, multiple phases, wells, nonlinear properties, and changing saturation, the system becomes large and complex. The simulator must solve a large set of algebraic equations at every time step. But the principle remains intuitive. Approximate the reservoir with grid blocks, calculate flow between them, and update the state through time. Now that we understand finite difference flow, let us move to initial and boundary conditions. Every reservoir simulation needs initial and boundary conditions. Initial conditions describe the state of the reservoir at the beginning of the simulation. This includes initial pressure, initial saturation, temperature, fluid contacts, and sometimes stress state. If the initial conditions are wrong, the forecast can be wrong from the very first time step. Boundary conditions describe how the reservoir interacts with the outside world. Some boundaries may be closed, meaning no flow can cross them. Others may be open or connected to an aquifer, allowing pressure support or fluid exchange. Boundary assumptions can strongly influence pressure buildup, plume movement, and production decline. The image on this slide shows a pressure field controlled by boundary behavior. This is very important in CO₂ storage and hydrogen storage. A closed reservoir may experience rapid pressure buildup during injection. An open aquifer may dissipate pressure more effectively. In geothermal systems, boundary heat flow can also matter. So before trusting simulation results, always ask, what initial condition did we use, and what boundary condition did we assume? Now that we understand initial and boundary conditions, let us move to well model, injection, and production. Wells are the connection between the surface operation and the underground reservoir. In simulation, a well can inject fluid, produce fluid, control pressure, or control rate. The well model translates operational settings into source or sink terms inside grid blocks. For example, a CO₂ injection well adds mass to the reservoir. A production well removes oil, gas, water, or brine. This slide shows pressure response around a well. Near well behavior is very important because pressure gradients are strongest near the wellbore. In practice, wells can be controlled by bottom hole pressure, injection rate, production rate, or constraints such as maximum pressure and minimum pressure. These controls determine how the simulator operates the well through time. For a beginner, the key message is this. Wells are not just points on a map. They are active boundary conditions inside the reservoir. They drive the entire dynamic response. If the well control is unrealistic, the simulation forecast may be unrealistic. This is why reservoir engineers spend so much time defining well schedules, completion intervals, constraints, and operational strategies. Now that we understand well model, injection, and production, let us move to time stepping and stability. Reservoir simulation is a time-dependent process. We do not only calculate the reservoir state once. We update it repeatedly as injection, production, pressure, and saturation evolve. This is called time stepping. At each time step, the simulator solves the governing equations and moves the model forward. The size of the time step is very important. If the time step is too large, the solution may become unstable or inaccurate. Sharp saturation fronts may be smeared, pressure changes may be poorly captured, or the nonlinear solver may fail. If the time step is too small, the simulation becomes very slow. Good simulators often adjust time step size automatically, smaller steps during rapid changes and larger steps when the system is stable. This slide shows how time stepping creates a sequence of reservoir states. For long-term CO₂ storage or hydrogen cycling, we may simulate years, decades, or even centuries. Therefore, time stepping is not just a numerical detail. It controls accuracy, stability, and computational cost. A good simulation balances all three. Now that we understand time stepping and stability, let us move to relative permeability. Relative permeability is essential for multi-phase flow. When more than one fluid exists in the pore space, each phase does not have full access to the rock permeability. Water, oil, gas, CO₂, or hydrogen must share the same pore network. Relative permeability tells us how easily each phase can flow as a function of saturation. For example, if gas saturation is very low, the gas may be disconnected and unable to flow effectively. As gas saturation increases, gas relative permeability increases. At the same time, water relative permeability may decrease because the gas occupies part of the pore space. This competition controls mobility, displacement efficiency, gas recovery, and trapping. The curves on this slide are not just theoretical. They strongly affect simulation forecasts. In CO₂ storage, relative permeability influences plume shape and residual trapping. In hydrogen storage, it affects injection and withdrawal efficiency. In oil production, it controls water breakthrough and recovery factor. This is why laboratory core flood experiments and history matching of relative permeability are so important. Now that we understand relative permeability, let us move to saturation front movement. When one fluid displaces another, a saturation front develops. This front marks the region where saturation changes rapidly. In water flooding, it may be the water front moving through oil. In CO₂ storage, it may be the CO₂ plume advancing through brine. In hydrogen storage, it may be the hydrogen gas front during injection and withdrawal cycles. This slide shows the movement of a saturation front. The front is controlled by injection rate, permeability, relative permeability, viscosity contrast, gravity, capillary pressure, and heterogeneity. In a homogeneous reservoir, the front may look smooth and symmetric. In a heterogeneous reservoir, it can finger, channel, bypass zones, or become strongly asymmetric. Saturation fronts are one of the hardest things for simulators and AI models to predict accurately because they can be sharp and nonlinear. Numerical diffusion can smear the front, while poor grid resolution may miss key details. For practical operations, the front tells us where the injected fluid is going, when breakthrough may occur, and how much storage or recovery is possible. Now that we understand saturation front movement, let us move to reading simulation outputs. A simulator produces many outputs, but the important skill is knowing how to read them. The colorful maps show spatial patterns such as pressure, saturation, temperature, or stress. The curves show time-dependent behavior such as production rate, injection rate, cumulative production, bottom hole pressure, or storage amount. When reading simulation outputs, we should not only look for beautiful images. We should ask physical questions. Does pressure increase near the injection well? Does the plume move in the expected direction? Does the production rate decline realistically? Is the mass balance acceptable? Are the boundaries influencing the result? Are there signs of numerical instability? For CO₂ storage, key outputs include plume footprint, pressure buildup, trapping fractions, leakage risk indicators, and caprock integrity. For hydrogen storage, key outputs include gas recovery, pressure cycling, cushion gas behavior, purity, and deliverability. For geothermal systems, we care about temperature decline and heat production. Good interpretation turns raw simulation results into engineering insight. Now that we understand reading simulation outputs, let us move to time stepping in simulation. This slide goes deeper into time stepping. In a reservoir simulator, time is advanced through a sequence of steps. At the beginning of each step, the simulator knows the pressure and saturation from the previous step. It then applies well controls, boundary conditions, fluid properties, and flow equations to calculate the next state. A key challenge is that the equations are nonlinear. Relative permeability changes with saturation, fluid properties may change with pressure, and wells may switch controls when constraints are reached. Therefore, each time step often requires iterative solution methods such as Newton-Raphson. The simulator keeps correcting the solution until the residuals are small enough. In practical terms, time stepping affects both accuracy and speed. If you simulate CO₂ injection over 30 years, you may not need daily time steps during quiet periods. But during the start of injection, shut-in, breakthrough, or operational changes, smaller time steps may be necessary. A strong modeler understands when to trust large steps and when to refine them. Now that we understand time stepping in simulation, let us move to boundary conditions matter. Boundary conditions can completely change the simulation outcome. Imagine injecting CO₂ into a closed box. Pressure builds up quickly because the fluid has nowhere to go. Now imagine the same injection into a large aquifer with open boundaries. Pressure can dissipate over a much larger region. The injection operation may appear much safer, even if the local plume is similar. This slide compares the effect of different boundary assumptions. The key lesson is that boundary conditions are not minor technical details. They define the physical environment around the model. In small sector models, boundaries are especially important because they may artificially constrain pressure or fluid movement. In full field models, boundaries may represent aquifer support, sealing faults, no-flow limits, or regional pressure sinks. For field-scale CCS and UHS, wrong boundary assumptions can lead to overestimating injectivity or underestimating pressure risk. When presenting simulation results, always describe the boundary conditions clearly. A result without boundary information is incomplete because the audience cannot judge whether the model is physically realistic. Now that we understand boundary conditions matter, let us move to wells control the system. Wells are the control handles of the reservoir system. By changing injection rate, production rate, bottom hole pressure, completion depth, or well placement, we can strongly change the pressure field and saturation plume. This is why well design and operation are central to reservoir management. The slide shows how different well controls create different reservoir responses. In oil production, the goal may be to maximize recovery while delaying water breakthrough. In CO₂ storage, the goal may be to inject as much CO₂ as possible while maintaining pressure below safe limits. In hydrogen storage, the goal may be to inject and withdraw gas over cycles while preserving deliverability and limiting losses. A very important practical point is that well controls can switch. For example, a CO₂ injector may start with a target injection rate. If pressure reaches a maximum bottom hole pressure limit, the simulator automatically reduces the rate. This behavior is realistic because field operations are constrained by safety and equipment. Therefore, when interpreting output curves, always check whether a well stayed on rate control or switched to pressure control. Now that we understand wells control the system, let us move to pressure diffusion demo. Pressure diffusion is one of the most intuitive phenomena in reservoir simulation. When we inject fluid, pressure increases near the well first. With time, this pressure disturbance spreads outward. The speed and shape of that spread depend on permeability, porosity, compressibility, viscosity, reservoir thickness, and boundary conditions. This slide shows a pressure plume expanding from the well. Notice that pressure diffusion may reach areas far beyond the visible saturation plume. This is extremely important for CO₂ storage and hydrogen storage. The gas plume may occupy a limited region, but the pressure footprint can be much larger. That larger pressure footprint can influence faults, neighboring reservoirs, or existing wells. Pressure diffusion also explains why pressure monitoring is powerful. Even if injected fluid has not reached a monitoring well, pressure may already respond. In field history matching, pressure data can reveal reservoir connectivity and permeability trends. So pressure is not only a flow variable, it is also a diagnostic signal for understanding the hidden reservoir structure. Now that we understand pressure diffusion demo, let us move to heterogeneity, changes everything. Real reservoirs are heterogeneous. This means rock properties vary from place to place. Permeability may be high in channels and low in shale layers. Porosity may change with depositional environment. Faults may act as barriers or conduits. Fractures may create fast pathways. Heterogeneity is one of the main reasons reservoir simulation is necessary. This slide shows that a homogeneous model and a heterogeneous model can give very different results. In a homogeneous reservoir, the plume may expand almost symmetrically. In a heterogeneous reservoir, the plume can move preferentially through high permeability pathways, bypass low permeability zones, and create unexpected breakthrough. This can strongly affect recovery, storage efficiency, and risk. For practical modeling, heterogeneity creates uncertainty. We rarely know the exact permeability distribution underground. We infer it from seismic data, well logs, core data, pressure tests, and production history. Therefore, a single deterministic model may not be enough. We often need multiple geological realizations to understand possible outcomes. This leads naturally toward uncertainty quantification later in the masterclass. Now that we understand heterogeneity changes everything, let us move from pressure to saturation fronts. This slide connects pressure and saturation. Pressure provides the driving force, but saturation shows where the fluids actually move and occupy pore space. During injection, pressure increases first near the well, creating a gradient. That gradient drives the injected phase outward. As the injected phase moves, it changes saturation in the reservoir. The important point is that pressure and saturation do not always have the same footprint. Pressure can travel faster and farther because pressure diffusion can occur through the connected fluid system. Saturation change requires actual displacement of fluid and movement of the injected phase. Therefore, the pressure footprint is often larger than the saturation plume. This distinction is very important for risk assessment. For example, in CO₂ storage, the CO₂ plume tells us where CO₂ is located, but the pressure footprint tells us where pressure-related geomechanical effects may occur. In hydrogen storage, saturation controls gas recovery, while pressure controls deliverability and operational constraints. A good simulation interpretation always looks at both pressure and saturation together. Now that we understand from pressure to saturation fronts, let us move to relative permeability, mobility competition. Here we return to relative permeability because it is so central to multi-phase simulation. The curves on this slide show how each phase becomes more or less mobile depending on saturation. This is the physical reason why saturation fronts form, why gas can become trapped, and why production performance changes over time. In a two-phase system, the total pore space is shared. When water saturation is high, water has good connectivity and flows easily, while gas may be disconnected. As gas saturation increases, gas pathways become connected and gas mobility increases. At the same time, water mobility decreases. This creates nonlinear behavior. A small change in saturation can cause a large change in mobility. Relative permeability is also strongly connected to hysteresis. The flow path during drainage can be different from imbibition. For example, gas injection increases gas saturation, but during water imbibition or withdrawal, some gas may remain trapped. This is especially important in CO₂ residual trapping and underground hydrogen storage cycles. If we ignore relative permeability and hysteresis, the model may give unrealistic plume and recovery predictions. Now that we understand relative permeability, mobility competition, let us move to capillary pressure and trapping. Capillary pressure describes the pressure difference between two fluid phases caused by pore scale forces. In simple terms, small pores can hold fluids strongly because of surface tension and wettability. This controls how fluids enter pores, how they displace each other, and how some fluid becomes trapped after flow reversal. In CO₂ storage, capillary pressure is important for caprock sealing and residual trapping. CO₂ cannot enter very small caprock pores unless pressure exceeds the capillary entry pressure. This helps explain why caprocks can seal buoyant CO₂. Inside the reservoir, capillary forces can trap disconnected CO₂ ganglia when brine flows back, creating residual trapping. For underground hydrogen storage, capillary pressure and wettability also influence gas distribution, recovery, and retention. In geothermal or water injection systems, capillary effects may be less visually obvious at field scale, but they still influence multi-phase displacement. This slide reminds us that simulation is not only about Darcy flow at large scale. Pore scale physics, such as capillarity, can control field scale outcomes. Now that we understand capillary pressure and trapping, let us move to CO₂ injection example. Now we apply the reservoir simulation workflow to CO₂ injection. In a CO₂ storage project, CO₂ is injected into a deep saline aquifer, depleted oil and gas reservoir, or other suitable formation. The simulator predicts how the CO₂ plume migrates, how pressure builds up, and how trapping mechanisms evolve over time. The slide shows a plume around an injection well. In the early stage, CO₂ accumulates near the well. As injection continues, the plume expands outward and may rise due to buoyancy. At the same time, pressure diffusion spreads through the brine-filled reservoir. After injection stops, the plume may continue to migrate, dissolve gradually into brine, become residually trapped, or eventually mineralize depending on geology and chemistry. For safety, the key outputs include plume footprint, maximum pressure, caprock integrity, fault stability, and leakage pathways. For storage performance, we care about storage mass, trapping efficiency, and injectivity. This example shows why reservoir simulation is essential for carbon neutrality. It allows us to design CO₂ storage projects that are both effective and safe. Now that we understand CO₂ injection example, let us move to underground hydrogen storage. Underground hydrogen storage is becoming increasingly important because renewable energy is intermittent. Solar and wind can produce excess electricity at some times and insufficient electricity at others. Hydrogen can store this energy chemically, and underground reservoirs may provide large-scale seasonal storage capacity. In simulation, hydrogen storage has special challenges. Hydrogen is a very light and mobile gas. It may migrate upward due to buoyancy, spread through high permeability pathways, mix with cushion gas, dissolve slightly in brine, or be affected by microbial and geochemical processes. The operation is also cyclic: injection during surplus energy periods and withdrawal during demand periods. The key simulation outputs include pressure cycling, gas saturation distribution, hydrogen recovery factor, deliverability, cushion gas requirement, purity, and trapping or loss. Compared with CO₂ storage, the goal is not only to store gas permanently. The goal is to recover hydrogen efficiently when needed. Therefore, reservoir simulation for UHS must focus on both storage integrity and operational performance. This makes it a fascinating and high-impact research direction. Now that we understand underground hydrogen storage, let us move to geothermal reservoir simulation. Geothermal reservoir simulation focuses on heat extraction from the subsurface. Instead of only tracking pressure and saturation, we also track temperature and heat transport. Cold water may be injected into a hot reservoir, heated underground, and produced back to the surface. The simulator predicts how pressure and temperature evolve over time. The slide shows a thermal plume, which is different from a saturation plume. In geothermal systems, a key risk is thermal breakthrough. If cold injected water reaches the production well too quickly, produced temperature declines and the project becomes less efficient. Therefore, well spacing, flow rate, fracture connectivity, permeability, and reservoir temperature are very important. Geothermal simulation also connects strongly with geomechanics. Cooling can change stress, potentially inducing fractures or seismicity. Pressure changes from injection and production also influence the stress field. This means modern geothermal simulation may require coupled thermal, hydraulic, mechanical, and sometimes chemical modeling. The broad lesson is that reservoir simulation is not limited to oil and gas. It is a foundation for many clean energy subsurface technologies. Now that we understand geothermal reservoir simulation, let us move to pressure can move faults. Pressure changes can influence faults. When pore pressure increases, the effective normal stress on a fault may decrease. This can make the fault easier to slip if shear stress is already close to failure. This is the basic mechanism behind some cases of injection-induced seismicity. The slide shows pressure interacting with a fault zone. In CO₂ storage, hydrogen storage, wastewater injection, geothermal systems, and even hydrocarbon production, pressure perturbations can change the mechanical stability of faults. This does not mean every injection project will cause earthquakes. It means pressure management and fault characterization are essential for safety. A coupled reservoir geomechanics workflow can estimate stress changes, Coulomb failure tendency, fault slip risk, and safe operational limits. Important parameters include fault orientation, in situ stress, friction coefficient, pore pressure, rock mechanical properties, and pressure diffusion. The main message is clear: simulation should not stop at flow prediction. For high-stakes subsurface operations, we must also ask whether the predicted pressure field is mechanically safe. Now that we understand pressure can move faults, let us move to uncertainty quantification. Uncertainty quantification asks a very practical question: how confident are we in the simulation result? In reservoir modeling, many inputs are uncertain. Permeability distribution, porosity, relative permeability, capillary pressure, fault properties, boundary conditions, and operational constraints may not be known exactly. If we run only one model, we may give a false sense of certainty. This slide shows multiple possible outcomes. Instead of one prediction, uncertainty quantification produces a range of predictions. For example, we may estimate P10, P50, and P90 outcomes for pressure buildup, plume extent, production rate, or storage capacity. This helps decision makers understand best case, expected case, and conservative case scenarios. Uncertainty quantification is especially important for CCS and UHS because safety and performance depend on uncertain geology. It also helps identify which parameters matter most. If uncertainty in permeability dominates plume prediction, we need better permeability characterization. If fault friction controls risk, we need better geomechanical data. So uncertainty quantification is not only about error bars. It guides data acquisition, monitoring, and risk-informed decisions. Now that we understand uncertainty quantification, let us move to history matching. Learn from data. History matching is the process of adjusting uncertain model parameters so that simulation results match observed field data. These data can include pressure, production rate, water cut, gas rate, temperature, seismic plume extent, or monitoring signals. The idea is to let the model learn from the real reservoir behavior. On this slide, the simulation curve is compared with observation. If the model does not match field data, we adjust uncertain parameters such as permeability, porosity, relative permeability, aquifer strength, or fault transmissibility. Then we rerun the simulation and compare again. This iterative process improves the credibility of the model before forecasting the future. However, history matching is not simply curve fitting. A good history match must remain geologically and physically realistic. Many different parameter combinations may match the same data, so uncertainty remains. This is why modern history matching often combines ensemble methods, Bayesian approaches, optimization algorithms, and machine learning. The goal is not to find one perfect model, but to find a set of plausible models that explain the data and support reliable forecasting. Now that we understand history matching, learn from data, let us move to optimization, find better operations. Once we have a working simulator, we can use it to optimize operations. Optimization asks, what decision gives the best outcome? In oil production, this may mean maximizing recovery or net present value. In CO₂ storage, it may mean maximizing injected mass while keeping pressure below a safe threshold. In hydrogen storage, it may mean maximizing deliverability and recovery while minimizing gas loss and pressure risk. The slide shows the idea of searching for better operational settings. Decision variables may include injection rate, production rate, well location, well spacing, completion interval, pressure limits, cycling schedule, or brine extraction strategy. The simulator evaluates each candidate strategy, and the optimizer searches for improved solutions. Optimization is powerful, but we must be careful. The best solution for one deterministic model may fail under uncertainty. Therefore, robust optimization is often more useful. Robust optimization tries to find strategies that perform well across many possible geological scenarios. This is especially important for subsurface energy projects where uncertainty is large and operational safety matters. Now that we understand optimization, find better operations, let us move to AI surrogate models. Fast forecasting. Reservoir simulation can be computationally expensive. A high-resolution model with multi-phase flow, geomechanics, geochemistry, or uncertainty analysis may take hours or days to run. If we need thousands of simulations for optimization or uncertainty quantification, the cost becomes very high. This is where AI surrogate models become useful. An AI surrogate model learns the relationship between inputs and outputs from a set of simulation runs. Once trained, it can predict pressure maps, saturation maps, production curves, plume footprints, or risk indicators much faster than the full simulator. This can accelerate decision-making, screening, optimization, and real-time monitoring. But we must use AI carefully. A surrogate is only reliable within the range of data it has learned. If we apply it to very different geology or operations, it may fail. Good surrogate modeling requires high-quality training data, proper validation, physical consistency checks, and uncertainty estimates. The goal is not to replace physics blindly. The goal is to combine simulation and AI so that we get speed without losing trust. Now that we understand AI surrogate models, fast forecasting, let us move to physics-informed AI. Respect the equations. Physics-informed AI tries to combine the speed of machine learning with the reliability of physical laws. Instead of training a model only to match data, we also encourage it to respect conservation equations, boundary conditions, physical constraints, and known relationships such as Darcy's law. This is important because pure data-driven models can produce outputs that look visually reasonable but violate mass balance or pressure constraints. For example, an AI model may predict a nice CO₂ plume shape, but if the total CO₂ mass is wrong, the prediction is physically unacceptable. Physics-informed learning adds penalties or structures that help the model stay closer to physical reality. However, physics-informed AI is not magic. Sharp saturation fronts, discontinuities, hysteresis, strong heterogeneity, and complex well controls remain difficult. In practice, the best approach may combine simulator-generated data, neural networks, conservation checks, finite volume residuals, and uncertainty quantification. The key message is this: AI should accelerate reservoir simulation, but it should also respect the equations that make the prediction trustworthy. Now that we understand physics-informed AI, respect the equations, let us move to monitoring. Update the digital twin. A digital twin is a living model of the reservoir that is updated as new data arrive. Instead of building one model and using it forever, we continuously compare predictions with monitoring data. If the model and data disagree, we update the model. This creates a feedback loop between simulation, field observation, and decision-making. Monitoring data may include pressure gauges, production data, injection data, seismic surveys, microseismic monitoring, temperature logs, tracer tests, satellite deformation data, or geochemical measurements. Each data type provides a different view of the reservoir. For example, pressure data may reveal connectivity, seismic data may reveal plume migration, and deformation data may reveal geomechanical response. For CO₂ storage, digital twins can support plume tracking and pressure management. For hydrogen storage, they can support cyclic operation and deliverability forecasting. For geothermal systems, they can support thermal breakthrough prediction. The future of reservoir simulation is not only running a model once. It is building a dynamic, data-updated system that supports safer and smarter operations. Now that we understand monitoring, update the digital twin, let us move to common mistakes to avoid. This slide is very important because many simulation errors come from modeling assumptions rather than software problems. One common mistake is using unrealistic boundary conditions. A closed model may overestimate pressure buildup, while an overly open model may underestimate risk. Another mistake is using a grid that is too coarse to capture key flow features, especially near wells or saturation fronts. A third mistake is ignoring heterogeneity. A smooth model may look clean, but it may miss the real preferential pathways that control plume migration and breakthrough. Another common mistake is trusting a history match without checking physical realism. A model may match production curves for the wrong reasons. Finally, many people focus only on attractive maps and forget mass balance, solver convergence, and uncertainty. The best practice is to always ask a set of quality control questions. Are the inputs reasonable? Are the equations appropriate? Are the wells correctly controlled? Is the mass balance acceptable? Are the results physically interpretable? Have uncertainty and sensitivity been tested? This careful mindset separates a reliable simulation study from a visually impressive but weak model. Now that we understand common mistakes to avoid, let us move to Masterclass Recap: what you can build. At this point, we have built the conceptual foundation of reservoir simulation. We started from the reservoir rock, then discussed porosity, permeability, pressure, saturation, Darcy's law, mass balance, grid discretization, boundary conditions, wells, time stepping, relative permeability, and simulation outputs. Then we extended the workflow to CO₂ storage, hydrogen storage, geothermal reservoirs, fault risk, uncertainty, history matching, optimization, AI, and digital twins. The most important message is that reservoir simulation is a system. No single component is enough. A beautiful geological model is not useful without correct physics. A powerful numerical solver is not useful without realistic input data. AI is not useful if it violates physics. Optimization is not useful if uncertainty is ignored. After this masterclass, you should be able to build a simple reservoir simulation workflow and explain why each component matters. In the remaining slides, we will reinforce the advanced concepts and connect them into a complete end-to-end workflow for modern subsurface energy projects. Now that we understand masterclass recap, what you can build, let us move to history matching. Here we return to history matching in a more applied way. The slide shows observed data and simulated data for pressure, oil production rate, and water cut. At the beginning, the model may not match the field data. This mismatch tells us that some assumptions are wrong or incomplete. The reservoir may have different permeability, stronger aquifer support, different relative permeability, or different well behavior than we assumed. The history matching workflow is iterative. First, we identify the mismatch. Second, we choose uncertain parameters that can reasonably explain the mismatch. Third, we adjust those parameters and rerun the model. Fourth, we compare again. Over several iterations, the model moves closer to the observed field behavior. But the goal is not to force a perfect visual overlap. The goal is to build confidence before forecasting. If a model cannot reproduce the past, we should be careful about trusting its future prediction. For CO₂ storage and UHS, history matching can use pressure monitoring, plume imaging, injection data, and production or withdrawal data. This makes the model more field-informed and more useful for real decisions. Now that we understand history matching, let us move to uncertainty matters. This slide emphasizes why uncertainty matters even after we have a calibrated model. The reservoir is never known perfectly. There may be many models that match the historical data but forecast different futures. One model may predict a small plume, another may predict a larger plume, and another may predict higher pressure near a fault. All of them may be plausible based on available data. This is why uncertainty should be part of the workflow, not an afterthought. We can generate multiple realizations of geology, rock properties, relative permeability, capillary pressure, boundary conditions, and fault properties. Then we run simulations for each realization and analyze the range of possible outcomes. For decision-making, this is very powerful. Instead of saying, the plume will be exactly here, we can say, under the current uncertainty, the plume is likely to remain within this region, but a conservative case extends farther. This is a more honest and useful statement. It helps design monitoring plans, safety margins, and robust operations. Now that we understand uncertainty matters, let us move to sensitivity analysis. This slide emphasizes why uncertainty matters even after we have a calibrated model. The reservoir is never known perfectly. There may be many models that match the historical data but forecast different futures. One model may predict a small plume, another may predict a larger plume, and another may predict higher pressure near a fault. All of them may be plausible based on available data. This is why uncertainty should be part of the workflow, not an afterthought. We can generate multiple realizations of geology, rock properties, relative permeability, capillary pressure, boundary conditions, and fault properties. Then we run simulations for each realization and analyze the range of possible outcomes. For decision-making, this is very powerful. Instead of saying, the plume will be exactly here, we can say, under the current uncertainty, the plume is likely to remain within this region, but a conservative case extends farther. This is a more honest and useful statement. It helps design monitoring plans, safety margins, and robust operations. Now that we understand uncertainty matters, let us move to sensitivity analysis. This slide shows optimization as a practical decision-making tool. In reservoir simulation, we often have many possible operational strategies. We can change injection rate, production rate, well placement, well spacing, completion depth, pressure constraints, cycling schedule, or brine extraction. It is impossible to test all possibilities manually, especially when each simulation is expensive. Optimization algorithms help search the decision space efficiently. They evaluate candidate strategies and move toward better solutions based on the objective. The objective might be maximizing CO₂ storage, maximizing hydrogen recovery, maximizing geothermal heat production, minimizing pressure risk, or balancing several objectives at the same time. In real applications, optimization should include constraints. We do not want the highest injection rate if it exceeds fracture pressure. We do not want maximum production if it causes excessive pressure decline or subsidence. We do not want a strategy that works only for one geological realization but fails under uncertainty. Therefore, modern optimization should be physics-aware, constraint-aware, and uncertainty-aware. That is where simulation becomes a decision support system. Now that we understand optimization, let us move to geomechanics and fault risk. This slide brings flow simulation together with geomechanics. When pressure changes in the reservoir, stress conditions can change as well. An increase in pore pressure can reduce effective stress, potentially moving faults closer to failure. Production can reduce pore pressure and may cause compaction or subsidence. Thermal changes in geothermal reservoirs can also modify stress. For fault risk, we often evaluate whether the stress state approaches a failure criterion, such as Coulomb failure. This requires information about fault orientation, in situ stress, pore pressure, friction coefficient, and mechanical properties. The reservoir simulator provides the pressure change, while the geomechanical model translates that pressure change into stress and stability indicators. This coupling is especially important for CO₂ storage, hydrogen storage, and geothermal development because public acceptance and regulatory approval depend on safety. A strong workflow should not only predict where the fluid goes, it should also predict whether the operation remains mechanically safe. This is how simulation contributes to responsible subsurface energy development. Now that we understand geomechanics and fault risk, let us move to monitoring and digital twins. Monitoring and digital twins are the bridge between simulation and real field operation. A simulation forecast is only useful if we can compare it with reality. Monitoring provides the observations, pressure, rates, seismic response, deformation, temperature, chemical signals, and sometimes microseismic events. A digital twin uses these observations to update the model over time. The slide shows the idea of a live model that continuously learns. At the beginning of a project, uncertainty may be large. As new data arrive, the model is updated, uncertainty can be reduced, and operational decisions can be improved. This is particularly valuable for CO₂ storage because operators must demonstrate containment and pressure safety. It is also valuable for hydrogen storage because cyclic operation requires continuous forecasting of deliverability and gas inventory. A digital twin is not just a dashboard. It is an integrated system of data, physics, AI, uncertainty, and decision rules. The future of reservoir simulation will likely be real-time or near real-time, where models are updated automatically and used to guide safe and efficient operations. Now that we understand monitoring and digital twins, let us move to AI surrogate models. This slide expands the role of AI surrogate models. A surrogate model is trained using many high-fidelity simulations. The input may include geology, permeability fields, well controls, injection schedules, or initial conditions. The output may be pressure maps, saturation maps, production curves, storage capacity, or risk indicators. The advantage is speed. Once trained, the surrogate can make predictions in seconds or minutes instead of hours or days. This enables rapid screening, optimization, uncertainty quantification, and interactive decision support. For example, we can test thousands of CO₂ injection strategies or hydrogen cycling schedules much faster than using the full simulator for every case. However, we should always remember that the surrogate is not automatically trustworthy. It must be validated on unseen cases. It must be checked for physical consistency, especially mass conservation and realistic plume behavior. It should also report uncertainty where possible. The best use of AI is not replacing the simulator completely. The best use is creating a hybrid workflow where physics generates reliable data and AI accelerates repeated prediction tasks. Now that we understand AI surrogate models, let us move to physics versus AI. This slide asks an important question. Should we rely on physics or AI? The best answer is not one or the other. Physics-based simulation is interpretable, grounded in conservation laws, and reliable when inputs and assumptions are correct. But it can be slow and computationally expensive. AI is fast and flexible, but it can fail when extrapolating beyond the training data or when physical constraints are not enforced. Therefore, the future is hybrid. Physics gives us the rules. AI gives us speed. Monitoring data gives us correction. Uncertainty quantification gives us confidence ranges. Optimization gives us decisions. When these elements work together, we can build powerful digital twins for subsurface energy systems. For your own research or project, do not present AI as a black box replacement. Present it as an accelerator, emulator, or assistant to physics-based simulation. Show that the AI model respects physical constraints, performs well on unseen cases, and provides useful decision metrics. This balanced view is much more convincing for academic papers, industry applications, and regulatory discussions. Now that we understand physics versus AI, let us move to end-to-end workflow. This slide summarizes the complete end-to-end workflow. We start with data, geology, seismic interpretation, well logs, core analysis, pressure tests, fluid properties, and operational history. These data are used to build the geological and simulation model. Then we assign physics, flow equations, relative permeability, capillary pressure, fluid properties, and sometimes geomechanics, geochemistry, or thermal processes. Next, we run the simulator and generate outputs such as pressure, saturation, rates, plume evolution, and risk indicators. We compare these outputs with field data through history matching. We then quantify uncertainty, run sensitivity analysis, and optimize operations. Finally, monitoring data are used to update the digital twin and improve future decisions. This workflow is powerful because it is iterative. It does not end after one simulation. Each new dataset improves the model. Each model result improves understanding. Each decision creates new observations. For modern CCS, UHS, geothermal, and reservoir management, this closed-loop workflow is the direction we should move toward. Now that we understand end-to-end workflow, let us move to final takeaways. Let us finish with the final takeaways. First, reservoir simulation is a virtual laboratory for the subsurface. It helps us understand what we cannot directly see underground. Second, the foundation is physics, porosity, permeability, pressure, saturation, Darcy's law, mass balance, and conservation equations. Third, numerical methods convert these physical laws into a grid-based model that can run on a computer. Fourth, simulation becomes truly useful when we connect it to real decisions: CO₂ storage safety, hydrogen deliverability, geothermal heat production, fault risk, pressure management, and monitoring design. Fifth, uncertainty is unavoidable, so strong workflows must include uncertainty quantification, sensitivity analysis, and robust optimization. Sixth, AI can greatly accelerate simulation, but it should be combined with physics and validated carefully. My final message is this: reservoir simulation is not just software. It is a way of thinking. It combines geology, engineering, physics, data, and decision-making. If we use it responsibly, it can support the next generation of clean energy and climate solutions. Thank you very much for watching this masterclass. Thank the audience, and invite them to subscribe or continue to the next episode.